Right now, like as you are listening to this, there is this invisible high-speed negotiation happening right in the palm of your hand.
Yeah, and it's totally silent.
Right. Completely automated. And honestly, if it stopped working for even like a fraction of a second, our entire modern world would basically just grind to a halt. We take it completely for granted.
We really do, yeah. I mean, we just assume we tap a glass screen and a high-definition video magically appears on command.
Right, like magic.
But underneath that glass, your device is constantly shouting into the digital void. It's asking for directions, proving who it is, and translating millions of ones and zeros into something you can actually use.
It's wild.
And it is doing this thousands of times a minute.
And that is our mission for this deep dive. Welcome in. I'm so glad you're joining us today. Today, we are going to demystify those hidden conversations.
Absolutely.
We're looking at this incredibly detailed slide deck from a CCNA networking course, specifically Module 15, which covers something called the application layer.
Right, the application layer.
And look, I know a Cisco Certified Network Associate curriculum sounds like it might be, a dry audio textbook. But stick with us here. We are going to translate this highly technical IT framework into an engaging roadmap of how the internet actually functions for you, the end user.
Because despite that technical sounding name, the application layer is the layer that sits closest to you.
Okay.
In the entire conceptual stack of network communication, this is the literal interface between the apps you open every single day and the underlying network wires and, well, invisible radio waves that actually carry the messages.
Right.
It is the bridge between human intent and machine execution.
So whether you are streaming a video on the couch, firing off a quick email at work, or even just like walking into a coffee shop and letting your phone automatically connect to the Wi-Fi, you are constantly relying on the protocols we're about to explore.
Yeah, it is the absolute foundation of your digital life.
So where do we start?
Well, to understand how it works, the source material breaks down network communication into conceptual layers. At the very top, closest to the user, is that application layer.
The interface.
Right. Its primary job is to act as the interface, exchanging data between programs running on the source host and the destination host. This is where famous protocols live, like HTTP for web browsing or DNS for name resolution.
Okay, let's unpack this, because the source actually mentions three top layers working together here: the application layer, the presentation layer, and the session layer.
That's right.
So if the application layer is just the interface, like handing off the data, what exactly are those other two doing to make the data usable?
Think about the raw data itself. The presentation layer steps in next, and it has three very specific crucial jobs to handle that data.
Okay.
First, it formats it. It ensures that the destination device can actually understand what is being sent. So if you're being sent a video file, it formats it as an MKV or an MPG so your video player recognizes it.
Oh, I see.
Yeah. Or if it is an image, it ensures it's coded as a JPG, a GIF, or a PNG.
So it's basically making sure I don't try to open a text document and just get a screen full of garbled static.
Exactly, that is the goal. Its second job is compression.
Making it smaller.
Right, it mathematically shrinks that data down so it can move efficiently across the network cables and then provides the instructions allowing the destination device to decompress it upon arrival.
Makes sense.
And its third job is security encrypting the data for transmission so it cannot be read in transit and decrypting it upon receipt.
So that covers presentation, formatting, compressing, encrypting, preparing the package, basically.
Yep.
What about the session layer?
The session layer is the manager of the ongoing conversation. It creates and maintains the dialogues between applications.
Like a supervisor?
Sort of. It starts the conversation, keeps it alive with automated keep alive messages, essentially pinging back and forth saying, "Are you still there?"
Okay.
And if the connection drops or sits idle for too long, it's the session layer's job to step in, recover, and restart that specific dialogue without crashing the whole application.
I want to try an analogy here to see if I've got this straight. Tell me if this works.
Go for it.
Is the application layer kind of like the physical restaurant menu you read to decide what you want?
Okay, yeah.
Then the presentation layer is the chef in the back taking the raw ingredients and actually prepping and plating the food so it's edible and recognizable.
I like this.
And then the session layer is the waiter coming by to keep your water glass full and ensuring the whole meal flows smoothly from start to finish.
That is actually a highly accurate way to visualize it.
Nice.
The menu is your interface, the chef makes the raw materials digestible, and the waiter manages the actual ongoing experience of the meal. But there's a crucial rule here that the source emphasizes for this whole restaurant to function.
Which is?
Both ends of the communication must speak the exact same application protocol.
They have to match.
They have to match perfectly. If your web browser is speaking HTTP to request a web page, the server on the other end absolutely must be running a web service that speaks HTTP in return. If they do not speak the same protocol, it's like speaking two completely different languages. The conversation just does not happen.
Which makes perfect sense. I mean, if the application layer is our menu and the session layer is our waiter, it makes me wonder who actually owns the restaurant.
What do you mean?
Like, are my phone and the server on equal footing in this exchange, or is someone clearly in charge of the transaction?
Oh, right. Well, that brings us to a major concept in the source material, the two main paradigms of network communication. We have the client-server model and the peer-to-peer model.
Let's start with client-server, because the curriculum implies this is what we use the vast majority of the time.
We do. In the client-server model, the roles are strictly, rigidly defined. The device requesting the information is the client. The device responding with the information is the server.
Okay.
The client always begins the exchange.
Right.
It initiates contact and says, I want this specific data.
And the server.
The server's entire job is to sit there, authenticate the request, find the requested data, and respond with a stream of information.
And this gives us our basic definitions of downloading and uploading, right?
It does. Data moving from the client up to the server is an upload. Data moving from the server down to the client is a download.
Got it.
The source gives a classic, simple example of this. A home email client requesting unread mail from an internet service provider's centralized mail server.
Right.
The email client is doing the asking, and the server is doing the delivering. The server has the authority and holds the resources.
Simple enough. But then the source pivots to peer-to-peer or P2P networks. And structurally, this sounds totally different.
It is a complete structural shift. In a true P2P network, there is no dedicated central server at all.
None.
None. Data is accessed directly from a peer device. Every single connected device on that network acts as a client and a server simultaneously.
Wait, simultaneously. How does a machine do both at once?
The roles are assigned dynamically per transaction rather than being fixed to the hardware.
Oh, I see.
So your computer might act as a server to share a piece of a file with someone for one transaction, while in the exact same fraction of a second, it is acting as a client, pulling a different piece of a file from someone else on the network.
Wow.
You are giving and taking at the same time, sharing the computational load.
The source mentions some very specific applications built on this, like BitTorrent, eMule, DC++, Dome Deluge.
Yeah, those are very popular P2P clients, often built on underlying protocols like Gnutella. They allow users to connect, locate, and access resources shared directly by the community of peers.
The source also mentions a hybrid model, which makes sense to me. I imagine you would still want some sort of central directory to tell you who actually has the files you're looking for, even if you download the files directly from the peers themselves.
You nailed the exact mechanism of the hybrid model. The actual resource sharing, the transferring of the heavy file is decentralized directly between the peers, which saves a ton of bandwidth.
Right.
But there is a centralized directory server that holds an index, like a map. Your client asks the central server, who has this file? The server points you to another peer's IP address, and then you connect directly to that peer to actually get the data.
I have a pushback question here then.
Yeah.
If peer-to-peer is so incredibly efficient, like it shares the load, there's no need to buy massive, expensive central servers or pay for all that centralized bandwidth, why do we bother with the client-server model at all? Why isn't the whole internet just peer-to-peer?
If we connect this to the bigger picture, it ultimately comes down to scale and control.
Okay.
P2P is very cost-effective and simple to set up in a small environment. But as the network grows, it becomes incredibly difficult to manage. There is no centralized control over where the data lives or who is altering it.
It's the Wild West.
It really is. And more importantly, it is inherently far less secure.
Why?
Well, in a client-server model, a company can lock down the server, build massive, complex firewalls around it, and rigorously authenticate exactly who has access to what data.
Right, that makes sense.
In P2P, you're opening direct connections to hundreds of unknown, unverified devices. For enterprise business, banking, or any sensitive data, that complete lack of security and centralized management is an absolute deal breaker.
That paints a very clear picture. P2P is fascinating for distributing public files, but the vast majority of our daily secure internet use relies on that traditional client-server model.
Exactly.
So let's look at the ultimate everyday client-server interaction. I want to walk through the exact anatomy of a click, what actually happens in the background when I decide to load a web page.
It is a beautifully complex orchestration, and the whole process starts with something called DNS, the domain name system.
Because computers don't understand words, they only understand numbers.
Right. Computers only speak in numeric IP addresses. But human beings are terrible at remembering long, arbitrary strings of numbers.
Yeah, I barely remember my own phone number.
Exactly. So we need what the industry calls FQDNs, fully qualified domain names.
Like www.cisco.com.
Yes. It is infinitely easier for you to remember Cisco.com than to remember its underlying IP address, which the source notes is 198.133.219.25.
Wow. Yeah.
So DNS acts as the Internet's automated phone book, translating the human-friendly name you type into the machine-friendly number the computer needs to actually find the server.
And when you look up a name, the DNS server doesn't just hand back a number blindly. The source says it uses specific tags called resource records to keep things organized.
The resource records are essential because they tell the system what kind of address it's handing back.
Okay.
For instance, if the lookup returns a standard IPv4 address, it categorizes that as an A record. If the server is using the newer, much longer format called IPv6, DNS labels that an APLA record.
And what if I'm not looking for a web page, but I'm trying to figure out where to send an email?
Then the DNS server will hand back an MX record, which stands for Mail Exchanger. It specifically points to the server authorized to accept email for that domain.
Incredible. So with those records in mind, the source details a four-step process that happens before a single pixel of a website even shows up on your screen. Walk me through that timeline.
Okay, so when you type a URL into your browser and hit enter, the browser realizes it has a name but no idea where that name lives. That's step one.
Right.
So for step two, your computer fires off a request to a DNS server asking it to resolve that URL into a numeric IP address. Once the DNS server hands back that A record with the IP address, your browser finally knows where it's going.
And that kicks off step 3, where the browser reaches out to that specific IP address and sends an HTTP GET request, basically knocking on the door and asking to view the web page, which is usually a file named something like index.html.
And finally, in step 4, the web server located at that IP address receives your GET request, processes it, and sends the actual HTML code back down the pipe to your device.
And then it shows up.
Right. Your browser interprets that code, renders the images and text, and you finally see the web page. All of that happens in a matter of milliseconds.
Let's pause on HTTP for a second, because the source points out it is a strict request and response protocol. And there are different types of messages we use to communicate. We just mentioned GTT, which makes sense. We're getting a page.
Yeah. The client is requesting data, asking to view a resource. But there is also POST, which is how you upload data to the server.
Like filling out a form.
Exactly. If you fill out a login form, enter a password, or complete a survey and hit submit, your browser uses a POST message to push that text up to the server.
Okay.
And then there is PUT, which is used to upload or replace a specific resource file on the server, like uploading a new profile picture.
The source makes a massive point about security here, contrasting standard HTTP with HTTPS.
Right.
This goes back to our earlier point about the presentation layer encrypting things.
This is a critical distinction. HTTP by itself is transmitted entirely in plain text. Yeah, if you send a password or a credit card number over standard HTTP, anyone who manages to intercept the network traffic between you and the server can just read it like a postcard. HTTPS, which stands for HTTP Secure, solves this massive vulnerability.
And how does it actually do that? Because it's still sending the data across the same public internet, right?
It uses the exact same underlying request and response process, but before the data leaves your device, HTTPS wraps the entire package in TLS or SSL encryption.
Okay.
Think of it like a mathematical scrambler. The client and server perform a complex digital handshake to agree on a secret key. Then, they scramble the data using that key.
Oh, wow.
If a malicious actor intercepts the data in transit, they don't see your password, they just see absolute mathematical gibberish. It provides authentication, proving the server is who it claims to be, and integrity, ensuring the data hasn't been tampered with.
Here's where it gets really interesting to me, though. Going back to DNS, the Internet's phone book, the source mentions a command you can run on your computer called nslookup to manually query these servers and see the records. But if every single click from every single person on Earth requires a DNS server to translate a name to an IP, how does the entire Internet not just crash instantly if a central DNS server goes offline?
It's a brilliant question, and the answer is that DNS isn't one giant monolithic server sitting in a heavily guarded room somewhere.
It's not.
No, it is a highly scalable, hierarchical system. It is broken down into small, manageable zones, structured like an upside-down tree.
So no single server has the entire map.
Exactly. At the very top is the root level. They don't know where everything is, but they know who to ask.
Okay.
Below them are the top-level domains, or TLDs, which you know as .com, .net, .org, or .edu.
Right, right.
Below that are second-level domains like Cisco.com. And finally, the leaf nodes, like www.cisco.com or mail.cisco.com.
So it's spreading the load out globally.
Every DNS server only manages the name-to-IP mappings for its own specific tiny zone. If a server gets a request for something outside its zone, it just forwards it up the chain to the correct server elsewhere.
That's incredibly smart.
It is. The resolution work is distributed across millions of servers, and to make it even faster, local servers and even your own Windows PC will cache or temporarily save the results of recent lookups.
Oh, I've heard of caching.
Yeah, you can actually see the saved local phone book on a Windows machine by typing ipconfig/displays in the command prompt.
Okay, so HTTP is the protocol for fetching web pages, and DNS is the map we use to find them. But what happens when we aren't just fetching a public page? What if we want to send a personalized, private message that sits waiting for a specific person?
Right.
That brings us directly into the digital post office email protocols.
Email operates on a fundamentally different principle than web browsing. It is a store and forward system.
Meaning my phone isn't actually handing the email directly to your phone.
Right. Email clients like your Outlook application or the Apple Mail app on your phone never actually talk directly to each other. They only communicate with centralized mail servers.
Okay.
Your messages sit in databases on these servers, stored safely, until your device specifically requests them to be forwarded down.
And the source outlines specific protocols for each direction of travel here.
For sending mail, we use SMTP, the Simple Mail Transfer Protocol. That handles moving the message from your client up to your server and then from your server across the internet to the recipient server.
That sounds pretty straightforward.
It is. An SMTP message is remarkably simple. It just needs a properly formatted header containing the sender and recipient addresses and a body containing the actual text.
But SMTP only handles the sending portion.
Exactly. To retrieve mail, you need a different protocol listening on a different channel. Historically, that was POP, the post office protocol, with POP3 being the most common version still referenced today.
Okay, POP3.
POP3 listens passively on a specific digital doorway called TCP port 110. When your client connects to that port, it downloads all the emails, and then, by default, it deletes them from the server entirely.
Okay, I have to push back here.
Sure.
In a modern world where you and I check our email on our phones, our tablets, our laptops, and our work computers, why would anyone ever want a protocol like POP3 that deletes the message from the server? It leaves no centralized backup.
Right.
If my phone downloads an email via POP3 and wipes it from the server, I'll never see that email on my laptop.
What's fascinating here is that POP3 is a legacy of an entirely different era of computing.
Oh.
When it was designed decades ago, mail servers had extremely limited, highly expensive storage space. They literally could not afford to hold onto your emails indefinitely.
Wow, so you had to clear it out.
Yes. The server was just a temporary holding bin. The expectation was that your personal local hard drive was the permanent storage solution.
But today, that architecture is a total nightmare for a multi-device user.
Which is why IMAP, the Internet Message Access Protocol, is the standard today. IMAP solves this modern problem by downloading copies of the messages to your client, leaving the original files untouched on the server.
So it's essentially making the client a real-time mirror of the server.
It creates a seamless synchronization. If you build a folder hierarchy on your laptop, IMAP mirrors it on the server and pushes it to your phone.
That is so much better.
Yeah, and if you read a message on your phone, IMAP syncs that read status back to the server so it shows up as read on your laptop too. It keeps everything in perfect harmony across as many devices as you own.
It is amazing how much engineering is happening in the background just to read a simple text email.
Seriously.
But there is a massive missing piece here. Web browsing, DNS lookups, sending SMTP emails. All of this relies on your device actually having an IP address in the first place so the network knows who is talking and where to send the replies.
Right. None of these application layer protocols work without an IP address anchoring your device to the network.
But when you walk into a coffee shop or a hotel and join the Wi-Fi, You never have to pull up a command prompt and manually type in an IP address. It just happens magically in the background.
That automation is handled by DHCP, the Dynamic Host Configuration Protocol.
Dynamic addressing as opposed to static addressing.
Exactly. Static addressing means a network administrator has to sit down at every single computer, open the network settings, and manually type in an IPv4 address, a subnet mask, a gateway router address, and a DNS server address.
That sounds terrible.
It is incredibly tedious, time-consuming, and highly prone to human error, like accidentally assigning the same IP to two different machines.
Right.
DHCP completely automates all of it. When a host connects, it asks for an address, and the DHCP server leases one to it from a pre-configured pool for a set amount of time.
The source breaks this automated negotiation down into a four-step process called DORA, D-O-R-A. Discover, offer, request, acknowledge.
Yep.
So what does this all mean in plain English? Let me try another analogy here.
Go for it.
It sounds like walking into a massive, crowded restaurant. You stand at the front door and you just yell, "Who has a table available?" That's the Discover broadcast, right?
Yeah.
Your newly connected device is broadcasting to the whole local network, looking for a server.
A loud approach, but yes. The client is shouting to see if any DHCP servers are listening.
Okay.
Then a waiter hears you, waves a menu, and says, "I have table 4 available for you." That is the offer step. The DHCP server replies with an offered IP address, along with the necessary subnet mask, gateway, and the duration of the lease.
Then I walk over to the waiter and say, "Great, I'll take table 4. That's the request. I'm accepting the specific offer."
Correct.
And finally, the waiter pulls out your chair, hands you the menu, and seats you. That's the ACK, or acknowledge. The server finalizes the lease, records it in its database, and your device is officially on the network.
That analogy perfectly captures the sequence of the DORA process.
But wait, what if 2 waiters wave at me at the exact same time? In network terms, what if 2 different DHCP servers hear my initial Discover broadcast and both send me an offer? How does the network keep from breaking?
That is exactly why the third step, the request, is so vital. The source clarifies that the client's request message explicitly identifies which server's offer it is choosing to accept.
Oh.
It effectively tells one server, "Yes, I accept your lease," and simultaneously tells all the other listening servers, "No, thank you, I have already secured an address."
So the other servers know they can immediately put their offered IP addresses back into the available pool for the next person who walks in the door.
And this strict sequence guarantees that no 2 devices ever get assigned the same IP address at the same time, preventing massive address conflicts that would completely crash the local network.
That is brilliant engineering, and it all happens in fractions of a second while you're putting your phone back in your pocket.
It really is wild.
Before we wrap up, there is one last piece of the application layer puzzle in the source: how devices actually share raw files with each other. The course contrasts FTP with SMB.
Yeah, so FTP, the file transfer protocol, is very straightforward. It was built purely to push data up to a server or pull data down from a server.
Simple enough.
It is a delivery driver dropping a package on your porch, upload and download. It is the classic rigid client-server relationship we discussed earlier.
But SMB, server message block, sounds like a much more integrated experience for the user.
It absolutely is. While FTP is a simple push or pull, SMB establishes a long-term persistent connection between the client and the server.
Okay.
Once your computer connects via SMB, the shared network folders, the files inside them, even a shared network printer down the hall, they all behave and look on your screen as if they are physically plugged into your own local computer.
Oh, wow. So you aren't just downloading a file, editing it, and uploading again. You can open a spreadsheet, edit the cells, and hit save, and it alters the file right there on the server seamlessly in real time.
Seamlessly. It essentially creates a portal on your desktop that reaches directly into the server. And it is not just a Windows exclusive tool anymore.
Really?
Yeah. The source notes that Linux and Mac operating systems can share resources with Microsoft networks using an open source implementation of SMB called SAMB. It is the underlying protocol that makes a modern corporate office network feel like one giant unified computer rather than 100 isolated laptops.
It is incredible how all these pieces fit together.
Mm-hmm.
Okay, let's pull all of this into focus. We have covered a massive amount of ground from this CCNA module.
We really have.
I want to remind you, the listener, of the absolute invisible symphony happening on your device right this very second.
It's constantly running.
To listen to this deep dive, your device used the DORA process in DHCP to lease an IP address. It used the DNS hierarchy to translate our web address and find the specific server hosting this audio file.
Yep.
It sent an HTTP GET request to download the data stream, all while the presentation layer is constantly formatting and decompressing the data so your speakers can actually play the sound you're hearing right now. It is genuinely breathtaking when you realize just how many automated rules have to execute perfectly for a single click to work.
It truly is a masterpiece of automated engineering. But, this raises an important question.
What's that?
All of these protocols, the DHCP leases, the DNS caching, the HTTP requests, they all fundamentally rely on devices playing nice. They rely on machines politely following the rules of automated negotiation.
Okay.
What happens to the security and stability of an entire network when a malicious device connects and decides to simply lie during these automated handshakes, claiming IPs it doesn't own or handing out fake DNS directions?
Oof. A rogue waiter giving away everyone's tables, or a fake phone book secretly giving out the wrong IP addresses. That is a terrifying but fascinating thought to leave on. Thank you for joining us on this deep dive into the application layer. Keep exploring the invisible world around you, and we'll catch you next time.